Hi, I'm Michael Paul, the Penn State Lunar Lion Team leader. I'm here in the Student Space Programs Lab with Michael Policelli. He's a senior here at Penn State, and he has since January been working on the project. I set him to the task of finding out which launch vehicles would be appropriate for this mission. And going into any mission concept study, you need to know not just what you're going to do when you get to your target. In the case of the X Prize, we've got to take the images and the video and so forth, but how are you going to get there? And knowing which launch vehicles could be appropriate is a key parameter going into the study, so that we know what our targets are for mass, and everything flows from that in any space mission. All the systems are interconnected, but this first question, how big is your spacecraft, how heavy is it, and which launch vehicles can get you to your target, is crucial to making sure that the mission study is a success and laying the groundwork for the whole rest of the program. And so we'll hear from Michael tonight about what it took and to figure out which launch vehicles would be appropriate and the other things that all kind of flow from that.
Hello, I'm Michael Policelli, a senior in material science and engineering here at Penn State, and I just want to talk a little bit about the logistics of our flight to the moon. The launch vehicle will put us on what's called a translunar insertion, which will get us up to the necessary speed to bridge the 400,000 kilometer gap in between the Earth and the moon. Even at that speed, which is about Mach 8, it's going to take 5.5 days of a coasting stage to get to the moon. Then once we approach the moon and we're relatively close to it, we're going to go into our two-stage descent. We're going to be using a solid rocket stage to eliminate most of the speed, and that's going to be an extremely tense amount of time, because in about 20 to 30 seconds we're going to go from Mach 8 to about 0 kilometers. We're going to be pretty much non-moving in space, and then we're just going to start to free fall. Then our liquid stage kicks in, and that's going to gently, softly land us on the lunar surface. I want to talk about a little bit about the criteria that allows us to choose the best launch vehicle for our mission and our team. There's a lot of criteria that you need to go through and really look at to choose what is the best launch vehicle. And the first one of that I would consider to be availability. There's a lot of different launch vehicles on the market, but some of them are not going to be used anymore by the time that we're going to be ready for our mission. For example, the Delta II, which has a capacity which is around what we're looking for and might have been an ideal choice, is no longer going to be in service, so we can't consider that. There's other launch vehicles that we know that are going to be coming online in a couple of years, but if that's not going to be ready in time for us, then we can't consider that. And the third point about availability is that when you're buying and using such a complex system as a rocket that has all these different stages and a lot of different challenges that are inherent with dealing with the different subsystems, then there can be some very lengthy lead times that could be a problem for a team to meet within the requirements of the Google Lunar X Prize Challenge. The next criteria that we need to consider is what the capacity of each of these launch vehicles is capable of sending to the moon. And that's not a trivial question to answer, because most commercial uses for satellites or for launch vehicles are going to be sending them into low Earth orbit or geostationary orbit. Geostationary orbit is where a lot of the communications and weather satellites are, but the moon is 10 times further than that. And that the further you want to send your rocket, the less mass it can take and it can carry to that. So I had to work with a lot of launch vehicle providers and really get their engineers to figure out what their systems are capable of to give us a solid number that we can base our mission design off of. And knowing how much mass that we can really work with is one of the most crucial aspects on mission design, because that controls everything else. There's been some recent missions in the past couple of years. I have sent satellites to orbit around the moon, but those satellites have not done a controlled landing, a soft landing on the moon that we are required to do. And because we're required to do a soft landing, we have to carry a lot of additional weight with our spacecraft when we're sending it to the moon, just to slow down and actually land on the moon. So this is a whole new game. This is something that hasn't been done in 40 years, and this is why this project is so complex, and this is one of the many challenges that we're facing. After we've gone through and figured out which launch vehicles are actually going to be available in our time frame and have contacted the companies and really gotten some solid numbers on what they're capable of, how much mass they're capable of sending to the moon, then another very important criteria for us to consider is the cost of each of them. If cost is no object, then we'd outfit a Hummer with electric motors and have it ramping around the moon with some cameras attached to it. But that's just not an option for our team. We want to have the most efficient launch vehicle option to meet our mission requirements. Once we've narrowed the field down to launch vehicles which meet the above criteria, then one thing that we need to consider is what the payload space that we need to fit into. In a rocket, the trunk of the rocket is in the right under the cone typically, and that can vary a lot between different launch vehicles. And if our final spacecraft design is wider than that cone, or wider than that tube that we need to fit in, then we need to have some sort of system that deploys. And whether it's arms that swing out or other things that move, anything that moves on a spacecraft adds an element of risk. And we'd like to avoid as much as possible any sort of complex system which can potentially fail. This has been a really exciting project to work on. If you told me 4 months ago that I was going to be sitting, talking about the complexity and the pros and cons of different rockets to send something to the moon, then I would have laughed at you, And in a very short period of time, I've gotten caught up to speed on all these things, and it's been very exciting and fun thing to do. And it's amazing how much you can learn if you just, keep asking questions. That's really what I'd say. Just, I have to just ask questions and really look online and look at different resources and lean on some of the professors here on campus, and in a short period of time you can really get up to speed with some things that it's rocket science. Well, this is rocket science, and it's been a lot of fun.